Let's look at the discrete frequency and time Fourier transform, or as it would be commonly known, the discrete Fourier transform, or just the DFT. So we've seen this type of image before. We've got 4 quadrants. Up in the top left hand quadrant we have our continuous time and frequency. So this is our normal continuous Fourier transform. So we see we've got an aperiodic continuous function in time, and whenever we Fourier transform it, we get a continuous aperiodic function in frequency. Now this isn't the actual Fourier transform of this, I've just idealised it for the moment just to help us understand what's happening. So if we were to look at the discrete time Fourier transform, then we would take the function of time here and we would sample it with this sampler here. When we multiply these two together, it would give us our discrete time sampled function here, f of nt. Now we know that whenever we multiply two functions together in the time domain, it's equivalent to convolving them in the frequency domain. So that's equivalent to taking this function f of I omega and convolving it with this impulse train here, st of omega. Now this impulse train here is just the Fourier transform of this impulse. So whenever we convolve these two together, it's equivalent to taking this function here and placing it at each of the spikes. So we're going to get this continuous and periodic function of frequency. So a discrete time Fourier transform takes an aperiodic discrete function of time here, and it produces a continuous periodic function of frequency, which you see here. So this here is the discrete time Fourier transform of this signal here. We then looked at the discrete frequency Fourier transform, which is shown in this quadrant up here. So now, instead of sampling the function of time, we're going to sample the function of frequency. So we do that by taking this function of frequency and multiplying it by this impulse train here. So whenever we multiply it by the impulse train, we get the discrete function f of I k omega naught. So now multiplication in the frequency domain is equivalent to convolution in the time domain. So if we were to take the time domain equivalent of these, well, the time domain equivalent of this one is this, and the time domain equivalent of this impulse train is this impulse train here. So we convolve this function of time with this impulse train, which is equivalent to taking the time function and placing it at each of the spikes. So we get this function here, which is a continuous and periodic function of time. So we can see then that whenever we are doing the discrete frequency Fourier transform, whenever we do the actual inverse transform going from frequency back to time, then we go from a discrete aperiodic function back to a continuous periodic function. So you can compare this here with what happened with the discrete time Fourier transform, and you can see the duality here. One of these surfaces, one of these functions is continuous and periodic, the other one is discrete and aperiodic, and again we've got one of the functions here is continuous and periodic, the other one is discrete and aperiodic. So that's a little summary of what we've done in the last two videos. We started off with a continuous time and frequency, then we went to a discrete time, and then we went over to a discrete frequency. So finally with the DFT, what we want to do is we want to be discrete in both time and also frequency. So we're going to get the forward and inverse discrete Fourier transform in two different ways. First of all, we're going to note that whenever we've got a discrete time Fourier transform, you can see that the frequency domain is actually continuous and it's periodic. So what we're going to do is we're now going to sample this function here. So if we sample this function here, it's the same as multiplying it by this impulse train. So whenever we multiply it with impulse train, we get this sampled function, which is going to be discrete and it's going to be periodic. So equally we're going to go in the other direction. You'll notice that whenever we did the discrete frequency Fourier transform, you get this function of time here, and this function of time is going to be continuous and periodic. So what we're going to do is we're going to sample this function of time. So we sample it by multiplying it by this impulse train here. And whenever we sampled it, we get this sampled function here, which again is going to be discrete and it's going to be periodic. So we're going to end up with a function here in this domain that is both discrete and periodic in time and also in frequency. So we're going to start off with the forward transform, and we're going to look at the discrete frequency Fourier transform, which gives us this transform pair here, and you can see there's only one of these is actually discrete and this is in the frequency. So what we're going to do is we're going to take this continuous periodic function of time and we're going to sample that, and when we sample that there, we're going to end up with this periodic and discrete function of time. So let's go ahead and we'll look at that now. So we're going to start off by looking at the forward transform. So what we have here at the moment is our discrete frequency Fourier transform, or more simply put, the Fourier series. So we're going to add up a whole load of sines and cosines in order to generate this continuous periodic function of time. So this is just really our Fourier series. This is the time domain and this is the frequency domain, and the frequency domain is integer multiples of a fundamental frequency omega naught. So now we're going to sample this here with this impulse train. So in effect we're just going to take this and multiply it with this impulse train, and we're going to get a discrete but periodic function here, which is our sampled function. But then what we have to do is we've got to go from the continuous time domain to a discrete time domain. So in order to go from the continuous to the discrete, we've got to use our conversion formula here. So we're using this conversion formula to go from here to here. And then finally we'll look and see how this is represented over just one of these periods. So this is us just windowed it over one period. So now if we look at the equivalent of this in the frequency domain, we're going to take these frequency domain components and we're going to convolve it with the impulse train here. So this impulse train here is the Fourier transform of this impulse train. So whenever we convolve this function here with this impulse train, it's equivalent to taking the function and placing it at each of the spikes. Now you'll note here as well that we already have a discrete function here, so it's the function of the discrete frequency k omega naught. So whenever we go from this line here to this line here, which in the time domain is equivalent to going from the continuous to a discrete variable, but in the frequency domain the variable is already discrete. So when we go from this point line through this line here to that line there, there shouldn't be any change in this function. Okay, so that function there is exactly the same as this function, and again we can window it and we can look at it over just one period. So finally what we're left with at the bottom here is the discrete Fourier transform. So this is going to be the forward transform. It's going to go from a function of time to a function of frequency. Now I know in this image that this function here looks just the same as this function, but it is actually different functions. It's just that I've idealized it a little bit in this example in order to get over the salient points. So a discrete function of time will give you a discrete function of frequency. So now we have an intuition of what's happening here with the forward transform. Let's go ahead and we'll derive it mathematically. So I wouldn't expect you to remember this type of derivation, but it's good to see it and work through it at least once, and then you know where to get it if you need to go and refer to it at any point in time. So this derivation here just follows what we've seen in the previous slide. So we take our function f of t, we sample it with this other function s of t, and this gives us our sampled function fs of t. Now the sampler here is the area sampler, which is just given by t, the sum from n equals minus infinity to infinity over delta t minus nt. So that's just our impulse train multiplied by our function f of t. So if we look above, that's just the first three sections of this. So it's our f of t times our sampler gives us our sampled function of time. So we're going to take our sampled function of time, and we've got to then perform the discrete frequency Fourier transform. So the discrete frequency Fourier transform takes our function of time, which is this whole thing here, and it multiplies it by e to the minus I k omega naught t. Now it's k omega naught because it's discrete frequency, it's a discrete frequency Fourier transform. And we integrate that from 0 to t naught of 1 upon t naught. But of course we've still got a factor of t here, so that becomes t upon t naught. Now this thing here, granted, looks like a bit of a monster, but what we can do is, first of all, the function here, f of t delta t minus nt times e to minus I k omega naught t, that function with the limits n equals minus infinity to infinity, that whole sum converges. Now we can use something called the dominated convergence theorem. Now we don't need to get into all the details of the analytics, but you can always look that up if you're interested. But that tells us then if this thing here converges, we're able to go and swap the limits of the summation and the integrand. So it means that we can then change this to the integral from minus infinity to infinity, and the sum from 0 to our value of t naught. So another thing to note in here is that we're going to introduce a new term, and this new term is going to be the factor of n. So this is large n. So let's go above and we'll see where we get the factor of our large n. So we can see here that our value over t naught is the period of this function of time, and the value small t is the period of the impulse train. So the period impulse train here is a lot shorter, that's t, than the period of the function here f of t, which is given by t naught. Now the value n is the number of samples in that period. So in this instance here, if you count them, there's actually from this point to this point here, which is just one behind the little pink dot, there's actually 10 samples. So those 10 samples will then be placed on the pink dot, and then they would repeat again and again and again. So our value t naught here can be given by the number of samples times the sampling period t. So that's going to be nt. So we're left with this little equation, t naught equals nt. So don't get mixed up with these. T naught is the period of the time domain function here, and t is the period of the sampler. So we have this t naught equals nt. So it means that this t upon t naught can therefore, from this equation, be replaced with simply 1 upon n. Also, you note that the upper limit of this integration here is going to be a value of t naught. Now that value of t naught there can be replaced by a factor of n minus 1. So let's go ahead and we'll have a look and see how we end up with that n minus 1. So n is the number of samples. So we're going to have, say, 10 samples from this point here to just this point here. But the actual samples are not defined from 1 to 10. They're actually starting off at 0. So they actually go from 0 to 9. So to get to this point t0, it's actually going to be a value of n minus 1. So that's going to be 10 minus 1 in this case here, which in effect would be our 10 samples. But the samples would start from 0 to 9, which would give us our 10 values. So it's really just about where we start counting the index here. Does it start from 1 or does it start from 0? In this instance, it starts from 0. So granted, this thing here doesn't really look any simpler, but what we can do is we can replace this integral here with the sifting property. Now if you're interested, there's a video on the Fourier and Laplace transforms on the sifting property, but let's just go ahead and we'll do the substitutions first of all, and then we'll talk about it. So what we want to do is we take this f of t e to the minus I k omega naught t, and we substitute that a function in for that, so we just call that g of t, so that whole thing becomes g of t, and we substitute the value nt with a value of tau. So that means when we do the substitution, this integral becomes the integral from minus infinity to infinity of g of t delta t minus tau by dt. Now this thing here is nothing other than the sifting property, and the value of this is just the value g of tau. Now this is actually quite simple. What it's telling you is that if you have a function g of t and you multiply it by an impulse, now it's a delayed impulse, so that impulse will only exist at a value of tau. So that means that whenever you multiply these two together, all you're going to get is the value of this function here at that point tau. So you're only going to be left with g of tau. So it means that this whole integral here can simply be written as g of tau, but our tau is nothing other than our nt. So it means that we can then write our g of nt is equal to f. Now the t is now the nt, so it's going to be f of nt, and the e to I k omega naught t gets replaced with the nt, so you're left with this factor here. So we can simply take this whole lot out and we can replace it with our f of nt e to the minus I k omega naught nt. So finally what we want to do is we want to take this function here and we want to convert it from our continuous time to a discrete time. In order to do that, we have to go through the conversion law. So this is the conversion law here. So when we put this through the conversion law, f of nt can then be replaced with our f of nt in square brackets, which tells us it's a function of a discrete variable nt. But we're also going to have this extra factor of t in the bottom line in order to do that. So finally we're left with this function here, f of I k omega naught equals 1 upon nt, the sum from n equals 0 to n minus 1 over f of nt e to the minus I k omega naught nt. And this is the function that we wanted to derive, which is going to give us our discrete Fourier transform, and it's the forward transform. But we're going to simplify this a bit as well and slightly change it so as it looks like the values, the function that you would tend to normally see in books. Now we can go through this similar process in order to get the inverse transform, but now what we're going to do is we're going to take the discrete time Fourier transform of a function. So we start off with our function here in the frequency domain, which is continuous and periodic, and we're going to sample it. So we're taking this and we're multiplying it with this, and we get our sampled function here. Now the equivalent to that in the time domain is this function here, which is convolved with this sample function here, and this is the convolved function. And then we've got to go from the continuous domain to the discrete domain. Now in this case here we're going through the conversion law, but the conversion law is the frequency conversion law, which is 1 upon t naught, f of I k omega naught equals f of I k omega naught. So the right hand side here, this is the discrete, and this side here is the continuous. So we end up with our two sets of graphs at the bottom here. So this is going to be our inverse transform. So it's going to go from our function of our complex, our frequency k, to a function of our time f of n. So that goes from f of k to our f of n. Now the mathematics is shown below, which again just follows the exact same route as we've seen here in the graphical approach. So I'll show you the mathematics here. Now the best thing to do is I'm not going to talk all the way through it because it follows the same route as the previous one, so it's a good exercise to work through the mathematics here. But you can see the similarities. We're going to have our function here, f of I omega times our impulse train delta I omega gives us a f of s. So in this instance this is the first three in this side here. Okay, so this one, f of I omega times delta omega is fs I omega. And then we work through the similar process here. We know that our S of omega is going to be given by the impulse train, and this is the impulse train here, is omega naught, sum from k equals minus infinity to infinity over delta omega minus k omega naught, and that's times our f of I omega. And again, we do this case here the discrete time Fourier transform, and this is us performing the discrete time Fourier transform on that function. And again, we're going to go and swap the limits round about because this function here converges. We can also change the limits here. We can change the omega naught upon omega s to 1 upon n, and again you can have a look there and you can figure that out and work that out there for yourselves. And again, we go through the same process of working through the sifting property, and the sifting property simplifies all the way down until we get our final inverse transform, which is going to be given by this function here. So again, we're going to go and take this and simplify it, so we'll do that next, and we'll have the two simplified forward and inverse equations. So if you have any problems with this or you want to talk over, you can always just send me an email and I can talk you through this derivation if you require. So this is the forward and inverse transforms that we've derived through this video, but we're going to go and simplify them now. First of all, this ik omega naught can be replaced simply by the f of k, and the nt can be replaced by n, because the k defines the actual samples in the frequency domain, and the n defines the sample in the time domain. Now also we can see that the omega naught is equal to 2 pi upon t naught, and we know that our t naught is equal to our nt, so we've seen these throughout the previous video. So it means that we can replace this omega naught here with our 2 pi upon t naught, but that in effect will be 2 pi upon nt. So it means that whenever we put the 2 pi upon nt in here, this t will cancel out with that t there, and we'll be simply left with e to the minus I 2 pi k small n upon large N. So we're going to have f of n e to the minus I 2 pi k small n upon large N. This is sum from n equals 0 to n minus 1. And also what we're going to do is we're going to normalise the sampling interval. So we call the sampling interval a value of 1. So it means that t there is going to disappear. So we just got the 1 upon n. We do the similar thing with the inverse transform and we get this function here. But a thing to note is that we don't generally see them written in the book in this form. They tend to have the 1 upon n over at the function f of n. So I've rewritten it in this format, but they're consistent in either format. But this is just the way you tend to see them written. So after a long video and a lot of mathematics, but hopefully with a bit of intuition as well, we've managed to derive the forward and inverse discrete Fourier transforms. Now what we want to do is go and actually use these, and from using them gain a real intuition as to how they work, and we'll also look at them in terms of the roots of unity, and we'll have a good graphical and intuitive understanding. So we'll get to that in the next video. So thank you for listening. I'll get you in the next video. Goodbye.